So I told you about two different kind of specific heat capacities in the last lecture, that is Cp and Cv. So I told you to look what this P and V means and tell. So basically there are, so in thermodynamics P and V are very obvious, it's pressure and volume. So pressure and volume are there. So Cp means specific heat capacity at constant pressure, and Cv means specific heat capacity at constant volume. Both of them are defined in a similar way, Cp and Cv, but the thing is Cp is used when the process is isobaric. So if process is isobaric, we should use Cp to be our specific heat capacity. And if process is so constant volume is isochoric. We should use Cv to be our specific heat capacity. Both are defined in a similar way, Q by mCp delta T, Q by m into delta T. So Cp is Q by m into delta T, and Cv is also. So keep it in mind, till now we are using small c, Q by m into delta T. Okay, so this is just a brief introduction about specific, why I started my lecture with saying specific heat capacities. And so because there are two kind of specific heat capacity, that is specific heat capacity at constant pressure and specific heat capacity at constant volume, and at any level, at any scale, we wanted to choose one out of the other, either pressure constant or the volume constant. We have to take out only these two specific heat capacities in our system. Okay. Okay, so let's look at molar specific okay. So molar specific heat capacity, as the name suggests, is molar. So currently the small Cp, the small c we have defined to be Q by m into delta T. So that is in terms of mass. Now, so this is small c. Keep this in mind. This is a small c. This is just a symbol, nothing else. So when I am saying molar specific heat capacity, I wanted, so that means that I should have to define a specific heat capacity in terms of moles. Okay, so instead of mass, it is for the moles. So how it is defined? It is like this: C, that is capital C, is Q by N into delta T. Okay, so can we relate these two? Yes, we can relate. So first I should define this. So this is molar specific heat capacity, capital C. So it is the heat required to raise the temperature of 1 mole of gas by 1 degree centigrade. Okay, so this is just centigrade, don't confuse it with anything else because of this discussion. So this is temperature of 1 mole of gas. The only difference is this 1 mole. Okay, at that when we are defining small c, we are saying it's unit gram or 1 gram or unit mass. Okay, but here it is 1 mole. So be clear about it. So let's relate the two C's. So can I write capital C in terms of mass? I can. So in terms of mass, so how N is defined? Number of moles is weight of the gas, let's say capital M, divided by molecular weight. Okay, so what symbol I should take for molecular weight? Let's say, so because I have taken so number of moles can be defined as weight divided by molecular weight. So this is molecular mass of. Okay, so N is this. So let's put this value here, M divided by M into delta T. So it is M into Q by M delta T. Okay, and I already told you what this is. It is nothing but small c. So capital C is M times of small c. So capital C is in terms of moles, that is molar, or I can write molar specific heat capacity. And this is in terms of mass. Okay, so this is the relation between two, and if I have to like two different specific heat capacities that I told you, Cp and Cv, for both the cases it is same. Okay, so I can write for your reference. So that is Cp is M into Cp, Cv is also m into Cv. Okay. So you will get questions on this, like the molar specific heat capacities and the interchange in the relation between the two. The relation between Cp and Cv is defined as R. Okay. So let's do one question. For oxygen, find out the value of Cp minus Cv. Options are 32R, R by 32, 16R, R by 16. Keep it this in mind. This is a small Cp minus Cv and this is normal specific heat capacity. Capacity defined in terms of mass. Make sure this should be there. So give it a thought. Let's take our time. So pause the video and try to solve it. So the solution to this is, so I have to find Cp minus Cv, that is small Cp minus Cv. So can I use this relation for solving this question? Yeah, I can. So small Cp is capital Cp divided by m minus capital Cv divided by m, and that is equals to R. No, actually it should be like this. So we know in terms of capital Cv what the relation is, and we can use that relation to find the relation between the small Cv and Cv. So capital Cp minus capital Cv is R. Now we can change it. So this is m into small Cp minus m into small Cv, that is R, and capital M is Cp minus Cv to be R, and Cp minus Cv is nothing but R by m. We know m is the molar mass. So you can use this relation for any of the question. For this question, we know molar mass of oxygen is nothing but 32. So the correct option for this is R by 32. I hope it is very clear to you, and let's discuss the heat in terms of specific heat capacities and how it is related to the degree of freedom. So relation between heat capacities and degree of So I have already discussed what degree of freedom is. I have already discussed what heat is, what heat capacity is. We have to just relate all of them together. Okay. So as I already told you, let's start with heat. So Q is N. So if I am saying QV, that is QCV delta T, and QP, that is NCP delta T. Okay. So CP and CV depends on, so capital CP and CV depends on degree of freedom. So I have already discussed what degree of freedom is, so I am not going to give details of all those things in this lecture. So but so how CP is related to the degree of freedom is this: CP is F by 2R, and we know CP minus CV is R, so CV is F by 2 plus 1 R, and so QV is N into F by 2 plus 1 of R, and QP is N into F by 2 into R. And we know for different kind of atomicities we have different degrees of freedom. So for monoatomic gases, F is 3, for diatomic gases F is 5, for polyatomic gases F is 6. So example of monoatomic are helium, neon, argon, etc. Diatomic is oxygen, nitrogen. CO2 also comes under diatomic because it's linear in nature. For polyatomic it's O3 and so on. So with this, in next lecture we will be going to discuss more on work, and I will give you some relation. So we'll try to find some values based on monoatomic and diatomic gases. We'll make form one chart so that it will be going into your mind, and that will help in your exam, that in your competitive exam, because that you should know directly. Okay, so thank you for that.